Alright, we got a electric field equation, and we want to find a streamline equation at some point. And then we also want to find, fix this wire, we also want to find a few different unit vectors. So let's get started. So whenever you're looking for a streamline, a lot of times you're going to run into the equation dy dx is equal to ey dx. This is just by geometry because you know, like this is the y components over the x. It's like the tangent of the function. So the reason this is useful is because we can now set a differential equation, solve it, and that'll give us a electric field line, and then we can plug it in for any point we'd like, and we'll be able to find the electric field line at that point, the equation for the electric field line at that point. So let's get started. Plug in ey and ex. So the y component is negative 15x squared y over this x component 5x cubed. So we can see right away that 5s will cancel, put a 3 up there, this x is going to be removed, that's going to be just an x. So now we have dy dx is equal to negative 3y over x. Okay, next thing we need to do is we're going to tackle this by using separation. One of the equations for, or one of the methods solving a differential equation. We basically treat this derivative operation right here as a fraction. Dy is equal to, we'll just divide the y. We'll bring this y over here like that, dy over y. And then we have this negative 3 over x, and then this dx will be multiplied through. So all I've done here, just to make sure I'm not losing anybody, I have divided this y and brought it over to this side, and then I have multiplied this dx and brought it over to this side. Okay? And you're not, you know, we're treating this as a fraction. It's really a derivative operation, but we can kind of do that. It works out in the math. So now we have two integrals, and relatively simple integrals at that. This will be ln y, and this will be negative 3 ln x, and we will put our constant of integration right there, okay? Because we're ultimately solving for y, so I just put the constant over there. Truly, both of these equations have a constant of integration, but you can lump them into one term, okay? So next we will raise everything to the e, so this will be e ln y, e to the negative 3 ln of x, and this will be e to the c. Or you can, well, to make it less confusing, I'll put plus c here. This is all in the power of e slot, you could say. So now these two will cancel. This will bring the y down, right? This this e and ln are going to cancel, so this is x. Actually, I'll write it like this first. Ln x, and instead of putting this plus c, we will do e to the c. But then you can realize that this e to the c is just equal to c, because we're only just worried about this is just some number. It doesn't really matter whether it's e to the c or c, because it's just a constant integration. So now we have y is c e to the negative 3 ln x, and then you can just bring out this x into the, you can cancel these, and it'll leave you with cx to the negative 3, essentially. Then y is equal to c over x cubed. All right, now this is the equation for the streamline. Streamline equation, right? So now we need to find the streamline equation at, or the streamline equation that passes through p is 4, 2, 1. So to do that, we plug in our y. So p is 4, 2, and 1. We will just plug in points. So y is going to be 2. Getting that right here. C is still unknown. It'll be c. And this 4 is going to be 4 cubed, because that's the x component. We're just plugging in the x component. So now c will be equal to 2 times 4. We'll put the times like that. Hopefully it's less confusing. 4 to the 3. That's going to be 128. So the final answer is y is equal to, you're just plugging in your c value now, 128 over x cubed. And this will be the streamline going through the point P. Okay? So now on to part B. We want to find unit vector specifying the direction of E at a new point Q. So now instead of a streamline, we just want to find the unit vector. Let me get a sip of tea. So to do that, we have our equation E is equal to, I'm just rewriting our equation, 5x cubed ax minus 15 x squared y ay. So now all we had to do is plug in our points at Q. So Q is equal to, or Q is, what's Q again? 3, negative 2, 5. Okay, so 3, negative 2, 5. So now we plug in our points Q and we'll get E of Q, right? Five, 3 cubed, ax, so 3 minus 15, 3 squared. This is negative 2, ay. So now simplifying, this is just simple math. This is going to be 135 ax minus. This is all going to, actually this negative and this negative will bring us to a plus term, positive term. And these three numbers, 15 times 3 times 2 is 270. So now, remember, we're trying to find the unit vector. And the unit vector is just the vector that we're curious about over its magnitude. So we have the vector right there, right? We just need the magnitude. So the magnitude of EQ is going to be, we just use our magnitude equation. 135 squared plus 270 squared. That will give us a value of 301.9, almost 302. And now you would just divide this vector by this. So EQ, all I'm doing is I'm going to take this term, I'm going to take 135 divided by 302, 301.9, and then 270 divided by 301.9. And that will leave us with 0.45 in the x direction and a positive 0.89 in the y direction. So now that's our answer for part B. Part C. Let's see what part C wants. I gotta read it again. A unit vector that is perpendicular to the electric field at Q. Or the electric field vector at Q, specifically. So we're looking for a vector perpendicular. And another thing to notice, oh shit. Come on, you stupid fuck. All right. Another thing to notice, get out of here, is it's asking for a zero z. It doesn't have a this unit vector that's looking for doesn't have a z. So we know that since this one doesn't have a z component either, both vectors are on the xy plane. And one way to find vectors on the same plane is you can find a normal vector, and then you can do a cross product of the two, and by the right-hand rule you're going to find a vector that's perpendicular. So like, let's say this is the xy plane. This is our EQ, right? We're looking for a vector that looks like this, right? It's perpendicular, but it's still in the same plane. Well, what we can do, let's say this is xy plane, right? What we can do is we use a normal vector. Pretend this is like sticking out of the page, kind of. Like this is like going up. This is straight in the z direction. So what's going to happen is if we cross product this and this, by the right-hand rule, we're going to find some vector. So actually, in this example, by the right-hand rule, our perpendicular vector would be in this direction. But it doesn't really matter. The point is, you're going to find, if you use this z and you cross product it with the vector you already have, you're going to find what you're looking for. Okay. So we'll do just that. So cross EQ and AZ. So if you want a different format to visualize things a little better, you're going to do 0.45. I'm just taking it from here. 0.89, 0. And you're going to cross that with 0, 0, 1. Okay? So that's exactly what we're going to do. So, oh shit. Sorry, I feel like I always do that. So when you cross product these two terms, I'll set it up in a more legit 0.89. And there's a million ways to do cross products, but this is how I do it. I would do 0.45. Oh wait, no, excuse me. I'd cross this one out. I'd like pretend this isn't there, so I do 0.89 times 1. And this would be minus 0. And that's the AX component. And then I'll put a minus sign. There's a million ways to do cross products. This is just how I do mine. 0.45 times 1 minus 0, so that'd be minus 0 AY. So that leaves us with a final solution of minus 0.5. Oh wait. All right, so there's your final solution, and yeah, hope that makes sense. You can see there's no z component, right? Because just like we said, it resides in the xy plane. Thank you. Bye.